Okay, I've come up with three conditional probability examples, the last of which is from the 2018 paper because it was something I hadn't really come across before. So anyway, here we go with a Venn diagram. I hope the start of this would be nice and easy. A union B is just everything in both circles, so not the 0.3, so that must be 0.7. B, well, hopefully watch my last video, which reminded you that the probability of A given B, we have the probability of B in the denominator, that's 0.4. And then we say of that probability, which part of it is down to A? That's 0.12. And 0.12 over 0.4, I'm sure that you're all ahead of me. That's 0.3. So similarly, the probability of B given A dash. So A dash is the probability that A doesn't happen. So that's these two together. Everything outside the A circle. So that's 0.58. And of that, what part is down to B? Well, 0.28. Of that probability, it's 0.28, which is down to B. So that's 0.28 out of 0.58, which is a horrible decimal number. And then probability of B, given that A union B has happened. So we've already answered A union B, so that's my denominator. And of that, what part is down to B? That's 0.4. So that is 4/7. Okay, sorry, it's evening, so that's why it's a bit swimmy. So here we've got a tree diagram. We're told the probability of A is 0.7, so that's got to be 0.3. The probability of B happening given that A has happened is 0.45, so that's got to be 0.55. And the probability of B happening given that A hasn't happened, 0.35, so that's going to be 0.65. So we can then work out the probability at the ends of all of these branches. This is all a bit GCSE, isn't it? But there we go, it's all good fun. And I'm then going to use those to answer the question. Of course, I know that all of these probabilities will add up to 1, which is, of course, is an important probability factor that's always true. 0.3 times 0.65. Okay. So the probability that A and B happen, 0.315. Probability that A doesn't happen and B doesn't happen, 0.195. This is the one I'm most interested in. So what's the probability of A given B? So I know that it's the denominator is the probability of B. So I'm not told the probability of B in the question. So what I have to do is look at my answer and say, right, which of these outcomes involve B happening? So the probability that B happens is those two added together. So is that 0.42? 0.42. So that's the probability that B happens. We're not given that in the question. I've just looked at which outcomes involve B and just added those probabilities together. Okay, that's the denominator of my fraction. Now, of those probabilities, which of them involve A happening? Well, this one doesn't, because this was A didn't happen. So it's this one. 0.315 out of 0.42, which is 0.75. And so then we come to question 5. This is on the 2018 stats paper. Now, if you look at the 2018 papers, it's one paper. What you'll get is what's been the case for the last couple of years, where you get a separate mechanics and stats paper. You can spend however much time you want on either, and it's not first hour is for stats, second half is for mechanics, but you've got to manage that, so you've just got to be really careful. Anyway, so we're dealing here with the lifetime of hours, which is modelled as a normal distribution with a mean of 18 and a standard deviation of 4. So, you know, this is my picture of what the distribution looks like. And so we're asked in the first instance to say, and that's the length of, that's the lifetime of a single battery. And so we're asked that here, what's the probability that a single battery has a lifetime that's greater than 16? And you know, it doesn't make any difference if you put the extras line under there. You know, the probability of having a lifetime of exactly 16 hours, not a nanosecond longer, not a nanosecond later, is 0. You know, so it doesn't actually matter. So I use my calculator for this. So stats, distribution, normal, cumulative. So firstly, making sure I get them the right way round, which I'm regularly not doing. So that's 4 is my standard deviation, and 18 is my mean. And I want to know the probability of greater than 16, so my lower needs to be 16. Now, do you remember for the upper, we know that the majority of the data is 3 standard deviations to the right of the mean, but actually, you can just put a massive number in there. You know, as long as it's big enough, you'll get the right answer. I'm expecting it to be more than a half, aren't I? Because the probability of 16 or more will be this side of the mean, and the probability of the mean up is a half. So I'm hoping this is going to be more than a half. Let's have a look. Bingo. So now I'm actually going to write that full number down. We have this problem, don't we, that we can't get values from the stats mode into our memories, which is a real shame. And I'm going to need this in a minute. Okay, so this is the bit where conditional probability comes in. At the start of her exams, she puts 4 new batteries in her calculator, and she uses them for 16 hours. And they've lasted. Okay? But now she's got another 4 hours of exams to sit. So let's consider one battery. So the probability that that battery will last 20 hours, given that it's already lasted 16 hours. So I can write that in the same way as in the 2 previous examples. It's the probability that the life is greater than 20 hours, given that it's already lasted 16 hours. So let's now do our denominator-numerator thing. The probability of greater than 16, that's what we've just worked out. So that's this number here. Now, of that, what probability is down to it lasting greater than 20? Well, let's look at, in fact, I'm going to grab a different colour. Hang on a minute, grab a different colour. So here's 20. So the probability that it lasts longer than 20 is this. Now remember what we say with conditional probability. We say, what's the probability of that? And of that, what part is down to this? Well, all of that is within that. So what I'm going to put in my numerator is whatever I get for the probability that it lasts longer than 20 hours. So I'm going to go back to my calculator and just change my lower to 20. Now I know this is going to be less than a half now because I've moved to the other side of the mean. So that's 0.3085, blah, 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 blah. And again, I would write down that exact value and get my answer. So in fact, I need to write down that exact value. So hang on a minute. 0.3085. So what I'm now going to do is come out of stats mode into my normal mode, and I'm actually going to work that out. So I've got, and of course this is a rounded value, but it's just a bit more accurate, isn't it? So I've got 0.30853753 divided by 0.69146246. Sorry, I've typed that in wrong. Hang on a minute. Missed out the 6. I get 0.4462, which at last I can now store in my calculator memory. Now, that's the probability that one of the 4 batteries lasts to 20 hours if it's already lasted 16 hours. So the probability that all 4 last, what's the probability of one thing happening and another thing happening and another thing happening? Well, this is just basic probability. It's that, times that, times that, and times that. So it's that to the power of 4. And that gives me the answer to that question. So conditional probability with the normal distribution is actually quite easy. The probability that it lasts 20 hours, given that it's already lasted 16, greater than 16 on the bottom, greater than 20, because all of that probability is included in the 16 probability. Okay.